there, and welcome to this Integrated Math 3 video series. This is Unit 2, and our first video in that unit. We're going to go ahead and start with our warm-up for today. So take a moment and see what you can do on these 5. Keep in mind that try to do some mental math as much as you can as you go. Okay, so number 1 here, what are the zeros of this polynomial? As we talked about last unit, this is factored form of this polynomial. We've got, let's see, 1 factor here, 2, and then this one's 2 of them in itself. So we really have 1, 2, 3, and 4. So this is a quintic, a quartic that we're talking about here. And what are the zeros of this quartic? So one of them is going to be -5. So really we just want to think about like what makes these parentheses 0. So what value of x could I put in here for x that makes it this 0? So it'd be -5 from there. This one's a little tricky because it's not just x plus or minus a number. We actually have to solve this one. So you could do this in your head if you could, or you could solve it just kind of on the side here. What makes this equal to 0? So it'd be 2x equals 1. X equals 1/2. 1/2 is the 0 from that one. And then lastly, we have 6 here, but because there's 2 of those factors, we say that there's a multiplicity. I'm going to abbreviate MULT. There's a multiplicity of 2 because there's 2 of those factors. So that means it's a double root. That just means it's going to bounce off the x-axis at 6. So that's all that means. So we have those 3 unique zeros, with one of them being a repeated or a double 0. Number 2, what is 81% of 2? A couple different ways you could do this. You could just double 0.81 if you wanted to. So if we double 0.81, we get 1.62. The other way you could do this is just to multiply 81 and 2 and get 162, and then adjust the decimal afterwards. Number 6 here, we have 3 times 4,312 over 3. You might think this is kind of difficult, especially if you try to do this division first. But in reality, what we can do is just divide the 6 by 3 first. And that ends up giving us 2 times the 4,312 that's left over here. So 6 divided by 3 is the 2. And then we can just double that and give us 8,624. So just kind of a different strategy there of doing that one. Number 4, if f of x is 2x squared minus 3x, what is f of -4? So again, we're going to put -4 in for all of these x's here, but be careful with your parentheses. Make sure you put parentheses around -4 as you put that in. So we're going to have 2 times -4 squared minus 3 times -4. Classic ACT type problem here. So -4 squared is 16. 16 times 2 is 32. And then -3 times -4 is +12, giving us 44. So f of -4 in this case is 44. And then lastly, number 5 here, we're going to spend a lot of time factoring today. So I wanted to go ahead and put a factoring problem on the warm-up here. In this case, we can factor using a greatest common factor. So we can factor out something here. If you think about the most that we can factor out from both of these have a factor of 4, and both of these have a factor of x squared. We can't take out any more than that. So we're going to take out a 4 times x squared, a factor of that there. So what we're left with here is, let's see, if we think about this as going backwards in like 4x squared times what gives us the 8x cubed back, it's going to be 2x. And then what will give us the 4x squared back, that should be a +1. So if we test this here, 4 times 2 is 8, x squared times x is x cubed, so that one's good. And 4x squared times 1 is 4x squared. So it's the same expression, just rewritten in a different form. So we can factor in that way. All right? So hopefully you're able to get those 5. Before we get into today's lesson, I do want to say that we have students in the room with us today, and so you might hear some questions being asked from them, or I might ask them to share their ideas. So just know that ahead of time. So for our lesson today, our goal is to rewrite various polynomials in factored form. So we're going to look at a lot of different factoring techniques. We're going to actually go back to integrated 2 for a moment and talk about quadratics. And then we're going to use our knowledge of quadratics to actually build upon that and look into factoring cubics and quartics and things like that. So that's our goal for today. All right, so let's go back to integrated 2, where you talked about factoring quadratics. So when we think about a quadratic here, x squared plus 7x plus 12, there are 2 types of situations with a quadratic that has 3 terms like this. The first situation is when a is 1. And now a is the value out in front of x squared here. It's not written, we assume it's a 1. So when that's the case, our factoring technique is actually quite simple. It's, we know we're going to factor into 2 binomials, and we just got to think about almost like reverse distribution. Like if we were to think about having two linear factors here, we'd multiply the first one times this first one, right? So what times what gives us the first term there, x squared? That would be x times x. And then if you think about distribution even further here, we're going to have x times this last term, and then this x times this last term. And both of those are going to give us like a linear factor of x. So you might have like 5x and 4x, or 3x and 2x, or something like that. Regardless, these are going to be like terms when we finish multiplying this out. We're going to have 2 multiples of x here that you're going to need to add to give us the 7x. But then also, the last thing we're going to do is multiply these 2 together. If you think about the FOIL, that would be the L, meaning last. These 2 multiplied together need to give us the 12. So all in all, these 2 numbers need to add to give us the 7x, or 7 I guess in general, and then these 2 numbers need to multiply to give us 12. So really it's just a process of thinking through the factors of 12. The factors of 12 are 12 and 1, 3 and 4, 6 and 2. We're going to think about which of those add to give us 7, and that's going to be the 3 and 4. So it'd be plus 3 and plus 4. So in this case, we're just kind of guessing and checking in a way, but just really going through the factors of the C value, 12, and thinking about what multiplies to give us the 12, but adds to give us the B value, which is 7 in this case. So hopefully that situation we're fairly good on right now. You don't need to do anything complicated with this. It's more of just a guess and check, trying to figure out what multiplies to give us 12 and adds to give us 7. From a visual representation, you can actually take algebra tiles and show this visually. So in this case, we've got x squared. So this has a side length of x and x, which gives us an area of x squared. So all of the terms we see here. So this is x squared, and then each one of these is x. It has an area of x. So this length here is just 1. So if we have length of 1, a width of x, then this area is x. If that makes sense. We have the same thing going on down here. Again, the length here is x, and the width is, in this case, is 1. So we have areas of x down here as well. And then all of these, this is a width of 1 and a length of 1. So all of these are 1 units. So this is just a 1, 1, 1. These are all 1s. How many 1s do you see there? 12 of them, right? So all in all, we have x squared. We have 4x and 3x. That makes 7x together, right? And then we have plus 12. So it's x squared plus 7x plus 12. But we've arranged these with 3 down here and 4 up here. And so what you can see here is that we've got all of these written out, but yet we can describe the side length. So the area of this whole thing could be the sum of all of its individual parts, which we have seen here, or it can be this side length. What is this side length here? X plus 3, right? We have x plus 1 plus 1 plus 1 is x plus 3. Across the top, we have x plus 4. So this area can be thought of as the sum of all of its parts, which is up here, or it can be thought of as the full length times the full width, which is the factored form. So just kind of an interesting way to think about visually factoring things here. So that's a equals 1. Hopefully you remember that from integrated math 2. Let's go on to a not equal to 1. Okay, so normally you would distribute this using what you typically call FOIL, but really it's distribution. But I want to show you maybe a different way here to start out. So instead of distributing this like normal, let's think about this. It's the same thing as 2x times this whole parentheses and 5 times this whole parentheses. Now normally we go ahead and distribute and multiply 2x times everything in those parentheses and 5 times everything in those parentheses. But let's go ahead and think about just first as 2x times 4x minus 3 plus 5 times 4x minus 3. So we see this is 2x times this whole parentheses and plus 5 times this whole parentheses. And then, of course, you would distribute the 2x in here and the 5 in here, just like you would with the distributive property, but this is kind of the in-between step. So I wanted you to see this because as we think about factoring here in a minute, we're going to try and reinvent this step as we go backwards. So let's distribute these in. 2x times 4x is 8x squared minus 6x plus 20x minus 15. And then, of course, the two middle terms are like terms, so we can combine those together to give us 8x squared plus 14x minus 15. So, what we want to do, when we start to do this next method where a is not equal to 1, we want to go backwards. We want to start with this. We want to separate this middle term back into these two separate ones, and then factor out a GCF from these two terms and these two terms to get back to something that looks like this. Right? If we were to factor out a GCF here, it would be 2x, and we'd be left with this left over. A GCF here would be 5, we'd be left with this left over. And then, once we get back to this, we can say, okay, what's a GCF of the entire expression here? And what's in common from both of these is the 4x minus 3. So we can actually factor out a 4x minus 3 from this entire line, and that'll leave us with something like that. So if we think about reverse distribution, it's going to really help us do this next type of factoring, which we call factoring by grouping. And this grouping comes in play right here, where we group the first two terms and the last two terms and factor out what we can. So I hope this will make more sense when we get to this problem here. So we have 8x squared plus 10x minus 3. And again, the first thing we want to do is separate the middle term. All right, y'all remember that from the last example? So we want to separate this 10x into two values that add up to 10x, but separately, all right? They're separate. So we're going to have 8x squared, and then we're going to have two terms in between, and then a minus 3 on the end. Here's how we figure out these two middle terms. Because you could separate into actually an infinite number of two terms, right? That add up to 10. But it's specific to what we want to do here. So 8 times negative 3 is negative 24. That is the new number that we want the two numbers to multiply to get. So we want to think about two numbers that multiply to give us this, add to give us 10. Okay? So this is kind of the new value that we want to multiply these two numbers to get. So it's by multiplying a and c, we get this new value. So can y'all think of two numbers that multiply to give us negative 24 to add to give us 10?
So it'd be positive 12 and negative 2.
Positive 12 and negative 2. Let's test it. Do those add, do we still have 10x here? Yes. And do those multiply to give us, let's see, 12 and negative 2 multiply to give us negative 24? Yes. So those are the precise two terms that we wanted to separate those into. So now we can actually group, it's called factoring by grouping. We're going to group the first two terms and the last two terms and factor out what we can from each. So what can we factor out from the, I'm just gonna underline it. Typically in the past, some students like to do parentheses, but it kind of gets confusing with parentheses and negatives and things like that. So I'm gonna recommend just underline the first two and the last two, and let's factor out what we can from each. So what can we factor out from this first group? Okay, 4, right? 4 goes into both 8 and 12, and what else? X. And what does that leave us with? 2x plus what? 3. Okay. All right, and then what can we factor out here? Yeah, a -1. So negative, I'm gonna write -1. I'm not just gonna write the minus. I'm actually gonna write the -1. You'll see why here in a second. It makes a little bit more sense for us here. All right, what do you notice? What's special?
They both have the 2x plus 3.
Yeah. When we factored out the greatest common factor, we were left with the same thing left over. And with factoring by grouping, that should happen every time. If you're not left with the same thing here and here, then something went wrong in the first step up here. So that should happen every single time, because now when we think about factoring out from the whole expression, we have something to factor out. What can we factor out from the whole thing now? What's in common from both factors? Yeah, 2x plus 3. So we can factor out 2x plus 3 out in front here. And we're left over, this additional stuff on the outside. So if we factor out a 2x plus 3 from this first term, we're left with 4x. If we factor out 2x plus 3 from this last term, we're left with a -1. So this exterior stuff here becomes our second factor. So do you see the connection between what we just did here and going backwards from here? Right? I mean, think about factoring by grouping. If we were to do this and go backwards, we would take 8 times -15. Let's see, 8 times 10 is 80, right? 8 times 5 is 40. Add them together, you get 120. So this is a -120. I would ask you what multiplies to give you 120, adds to give you, or -120 adds to give you 14, but our answer's already here, right? It'd be -6 and 20. And so that's how we would get these two terms, and of course we'd factor out the 2x from there and the 5 from there, and then we factor out a 4x minus 3 from both, and we get back there. So I hope you see the connection between the distributive property and what we're doing here called factoring by grouping. Now I teach you this method not just because it's good with quadratics, but because it's applicable to other situations as well. So anytime you can have an even number of terms, you can try factoring by grouping. It won't always work, but you can try factoring by grouping. So when I say an even number of terms, like here we started with 3 terms, but we turned it into 4, right? And then what happens when we have we'll come back to that one here in a second. What happens when we have a cubic? It's got 4 terms already. So we don't even have to separate the middle term. We've already got the 4 terms. So we can go ahead and start by grouping the first 2, the last 2, factoring out what we can. So we'll come back to that here in a minute, but I want you to know that factoring by grouping is not just for quadratics. It's applicable to a lot of things. So let me give you a chance to try this one using factoring by grouping. So take a minute and try and see if you can do that. All right, so this is, again, a factoring by grouping situation here because the A value here is not 1. So we have to go to the factoring by grouping method. And in fact, in this case, we're trying to find, when we split this middle term up, we're trying to find 2 numbers that multiply to give us -30, that add to give us this positive 13. So that's going to be, what did y'all come up with there?
Positive 15, -2.
Yeah, positive 15 and -2. And you might be wondering at this point, did it matter the order in which I put these? And it doesn't. The only thing that's going to impact on the end is the order of things in the end. But it's not going to change much at all. So it does not matter. All right, so now that we've split the middle term there into two, now we can factor by grouping. So we're going to group the first two terms here and the last two terms and factor out what we can from each one. So what can we factor out from the first two terms? 3x. And then what's left over as a result?
2x plus
2x plus 5, which makes sense because what can we factor out here?
-1.
A -1 again, leaving us with 2x plus 5. Did anybody switch the order of these? And you probably got 3x minus 1 left over here and here, right? And 2x out in front here and plus 5 out in front here. But you'll end up with the same thing. So what can we factor out of the entire expression now?
2x plus 5.
Yeah, 2x plus 5 times 3x minus 1. And at this point, if you want to check your answer here, just multiply this out and see if you're left with 6x squared plus 13x minus 5. So you can always check yourself that way. All right, so I hope that gives you another good example there of factoring by grouping with a quadratic. Let's try one more. This is a little bit different just because the leading term there, the 15, is negative in this case. So take a moment and see if you can try that one. All right, so in this scenario, we're wanting to find two numbers that multiply to give us positive 30, and add to give us 11. So same number there, 30, but a different set of factors here that are going to work. It's actually going to be what?
5 and 6.
5 and 6, yep. So it's going to be negative 15 x squared plus 5x plus 6x minus 6, or minus 2. Again, the order does not matter in which you do those. Let's see, in the first two terms, we can factor out, what, 5x? Okay. That leaves us with negative 3x minus plus 1. And then here,
2.
yeah, you can factor out a negative 2. So there's a couple of ways you can do it. You could have factored out a negative 5x here if you wanted to. It doesn't matter, either way is fine. So I factor out a negative 2 here, because you want it to be left over with the same thing that you have over here. So negative 2 does that, because negative 2 times negative 3x is still 6x. And then plus 1, because negative 2 times 1 is still negative 2. And then from there we can factor out a negative 3x plus 1 from the entire expression, leaving us with 5x minus 2. So any questions on factoring by grouping with quadratics? Yes?
If you did it the other way, were you supposed to get 3x minus 1 and then negative 5x plus 2?
Yes. If you did it the other way, so if we factor out a negative from here, we're going to be left with 3x minus 1. So that's one way to write it, is like that. So that would be a great way to write it. Or I think you would get your version if you distribute that negative into that parentheses. So yeah, all three versions would be the same. This is probably, thinking more about it graphically, this is probably the best version, just because we can tell the zeros pretty easily. This is going to be 2/5. This one's going to be 1/3 if you solve those. But this negative here tells us it's opening downward. And so you can kind of see it a little bit easier in that form. So yeah, good question. All right, so let's go on to taking this idea to a cubic. So this is a standard form of a cubic. And if we're looking at this right now, we can't graph this and know anything about the graph except for the y-intercept, which is negative 21, and the concavity, or sorry, the in behavior, which is going to be down to the left and up to the right. So I want to give you a chance to try this one without telling you how to do it necessarily right away. Try this one using factoring by grouping, only this time the middle term is already split up. Like we don't have a middle term anymore. It's already 4 terms. So go ahead and group them and see what you can do. All right, so with this cubic, again, we have 4 terms starting out. It's actually in some ways a little bit easier than a quadratic So when we group the first two terms, what did y'all factor out of the first two terms here?
2x squared.
2x squared, and that leaves us with?
X plus 3.
Yeah, x plus 3. And then what can we factor out here?
Negative 7.
-7. And let's make sure it leaves us with the same thing here, x plus 3. And just double check, -7 times x is -7x, -7 times 3 is -21. So that works, right? So now what can we factor out of the entire thing? X plus 3. Leaving us with
2x squared minus 7.
2x squared minus 7. Now keep in mind, this idea of factoring by grouping does not work for every single cubic in standard form. But it's one of the only ways that we had to factor a cubic in standard form. So keep that in mind, but know that it doesn't work every time. So just it's one way that we definitely want to check. So with that, now that we've done one example with this, go ahead and try this one and see what you can do. Okay, so on this one, what can we factor out of the first two terms?
X squared.
X squared, that leaves us with x plus 4. Yeah. And then the last two terms? 3, leaving us with
X plus 4.
x plus 4. So now we can factor out x plus 4 from the entire thing, leaving us with x squared plus 3. Any questions on that one? Okay. All right, so that was our goal for today, was mainly factoring by grouping, but thinking through like how do we factor a quadratic, how do we factor a cubic, and using this idea of factoring by grouping to rewrite polynomials in factored form. So that's it for this first video in Unit 2 of Integrated Math 3. In our next video, we're going to expand on this idea and look at a different form of factoring called difference of two squares. So we're going to do that in our next video.